Welcome back to your next lecture in Physics 235. This is week 12, day 1, scheduled for release on April 6th, and today we're going to be talking about light as a particle and specifically exploring the phenomena of reflection and refraction of light. So just a reminder, quiz 10 is due today, so if you need an extension on that, make sure you're emailing me to spend a late pass. Today is our first day working out of Volume 3 of our textbook, and we are going to be covering Volume 3, Chapter 1, Sections 1 through 4. Section 1 talks about, among other things, some historical measurements of the speed of light and how those were accomplished. I don't need you to know any of those ways that the speed of light was measured historically. All I really need you to know is the value. And the value for the speed of light is as follows. 2.99792458 times 10 to the 8th meters per second, which simplifies quite nicely to about 3 times 10 to the 8th, within less than a percent. Just a note that this is the speed of light in a vacuum specifically, so when light is traveling through the depths of space. It will turn out that when light travels through a medium like water or air or glass, it slows down by some factor known as the index of refraction. So this gives us a formula to define the index of refraction, which will become important going forward, as the index of refraction n equals the speed of light in a vacuum c divided by whatever speed light travels in that medium. Given that light will always slow down when it enters a medium other than vacuum, this means V will always be less than C, so all of the values of n that we're going to be dealing with are all going to be greater than or equal to 1. You can look at table 1.1 in your book for some common values. Generally, I'll provide you the index of refraction values you need for test problems and quiz problems in the problem statement, but for the homework, you might need to look some of them up in table 1.1 in the book, but I'm at least going to put some common values down here for you. The index of refraction of air is slightly higher than 1, but not by much, so for many of our calculations, we'll just take the index of refraction of air to be 1, which is the same as the index of refraction of vacuum. The index of refraction of water is around 4/3, and the index of refraction of glass is around 3/2. Note that these are all at specific temperatures, and for the gases at specific pressures as well. So the value of the index of refraction of air, of water, of glass will all change slightly depending on the temperature or pressure of whatever medium we're dealing with. So all of this sets us up to start to talk about the ray model of light. And the ray model of light is the counterpart to the wave model of light. If light acts like a wave sometimes, it acts like a particle that travels in straight line other times. And this straight line particle version of light is called the ray model. A lot of solving physics problems that have to do with light is in determining which model, the ray model or the particle model versus the wave model of light, is more appropriate for the situation that we're studying. And the ray model of light is most applicable when light is interacting with objects that are many, many times the size of that light's wavelength. Given that visible light has wavelengths in the hundreds of nanometers, so even that is still less than 1 micrometer, less than 1,000th of a millimeter, most everyday objects like glasses or fish tanks or camera lenses are already many, many, many times the size of visible light's wavelength. So we're going to end up using the ray model for a lot of macroscopic phenomena related to light. And the two phenomena of light that I want to talk about first are reflection and refraction. Reflection is when light bounces off of a surface. And refraction is when light passes from one material into another, or from one medium into another. And we're going to talk about reflection first, and then we're going to talk about refraction and some of the interesting effects that come along with each of them. So to begin with reflection, we're going to begin with the law of reflection, which states that when light bounces off of a surface, the angle of incidence equals the angle of reflection. So to give an equation and a diagram to this, the equation is just theta incident equals theta reflected. And you might have a diagram that goes with it that looks a little like this. This little line with those tiny little diagonal lines next to it that I just drew is intended to represent a mirror, where the flat line is the smooth surface of the mirror. So if we have light coming in towards this surface, it'll be coming in on some straight line path, traveling this direction, and this is referred to as the incident ray. And then that light will bounce off of the mirror, creating what's called the reflected ray, which will travel up this direction. And the angle of incidence and reflection are defined as follows. Both of these angles are measured with respect to the normal line, or a line that is perpendicular to the surface of the mirror. So theta incident is this angle right here, and theta reflected is this angle right here. There's a couple of phenomena related to the law of reflection that I want to discuss specifically. One of them is the difference between reflection off of a smooth surface and reflection off of a rough surface. So let's consider those two situations. So if we imagine shining a flashlight onto this surface, we might have our flashlight up here pointing this direction, and rays are coming out of that flashlight. And I'm just going to draw 3 of them. One here, and one here. Mostly parallel, but generally all traveling in the same direction. And each of these light rays will obey the law of reflection when it bounces off of that smooth surface. So the angle of the incident ray from the normal will be equal to the angle of the reflected ray from the normal, and the rays will be reflected out this direction. So if you're standing near this smooth surface, which might be the completely still surface of a pond, or maybe just a mirror that someone has left on the floor, you may or may not be able to see the flashlight. So if you were standing, for example, right here where this little green stick figure is, you would see the reflection. But if you were standing somewhere else, say over here, well, none of those rays are passing by you, so you can't observe that light and you do not see the reflection from this location. This situation is called specular reflection, though I don't expect that vocab will come up very often in the course. A good example of specular reflection might be if you're watching the sunset or looking at the moon over the surface of a completely still pond. You'll see a bright circle where the moon is reflecting off of the pond at only one location, but if you look anywhere else along that pond, all you're going to see is just the dark surface of the water. So, what if we had this same idea of shining a flashlight onto something, but instead of a smooth surface, we used a rough surface? Maybe this rough surface is some sort of bent piece of metal. Maybe it's just an everyday object like a tree or something that doesn't have a perfectly smooth surface. We can still shine light onto this surface and it will still obey the law of reflection, but a couple of interesting things happen. So let me draw the flashlight to try to explain this. So here we have our flashlight again, and I'm going to draw 5 rays coming out of this flashlight. Now each of these 5 rays by itself will obey the law of reflection, but note that the normal is pointing in a different direction at each of these locations. So here, this ray strikes almost aligned with our normal. But a lot of these other rays are not, oops, that's not a very good one, are not well aligned with the normal lines. So these little blue lines here are the normal to the surface of the mirror at those different locations. So each of these rays will be reflected off into the distance in some direction. Doing my best to make this to scale. Oh, and it looks like this ray is going to hit the mirror one more time. So you could see that the light here is scattered in every direction. So it doesn't matter where you stand, whether here or here or here, you're going to see bright spots on the surface of whatever this rough surface is, pretty much no matter where you stand. And this process is called diffuse reflection. So diffuse reflection is why if somebody shines a flashlight onto a piece of paper, you can see the bright spot created by that flashlight no matter where you're standing near that piece of paper, because the surface of paper is not mirror smooth. If you zoom in far enough, it's very ragged and uneven, and so you get diffuse reflection. Actually, most real-life objects give you diffuse reflection other than things that are very specifically designed to be smooth. Just a couple more notes about things related to reflection. One of them is how we can see ourselves in mirrors as a result of reflection. And when you see yourself in the mirror, what you are seeing is the rays that travel from whatever part of your body you're looking at to your eyes. So in terms of a diagram, that might look something like this. We have our mirror with the reflective surface facing towards you, and then we have you, the beautiful stick figure, and I'm going to draw the eyeballs of the stick figure here. And so if you're going to see your feet in the mirror, a light ray must have traveled from your feet to your eyeballs in straight line paths, obeying the law of reflection, so this angle is equal to this angle, and that is how you are able to see your feet in the mirror. The last thing I want to talk about related to reflection is something called a corner reflector or a retroflector. And these are mirrors that are designed with a 90-degree bend in them. So when light comes into this corner reflector, it is actually reflected back out parallel to how it came in. So the light might come in this way, reflects off of this surface, then reflects off of this surface, and goes back out that direction, where this angle is equal to this angle, and this angle is equal to this angle based on the law of reflection. But note that the angles with one tick in them are not equal to the angles with two ticks in them. It'll actually turn out, with this corner being 90 degrees, that this angle will be equal to our first incident and reflection angles, and this angle here will be equal to our second incident and reflection angles. But the point of this is that the reflected light leaves parallel to the same direction the light came in. This means that the light is sent back from the direction which it came. So this is very useful for things like bicycle reflectors or those reflective vests that construction workers wear at night. Because when your headlights from your car shine onto a corner reflector style surface, that means the light gets sent right back to you. So it seems like the person or the reflector on the bicycle is glowing and you can see them much easier. There's also a retroflector that astronauts left on the moon. So if you line up your laser just right, you can shoot a laser at the moon and it will be reflected back at you. And you don't have to worry about whether you're shining the light perfectly normal to the mirror on the moon because it's a retroflector. There are actually retroflectors made out of just metal, steel, or iron on boats that are used to send radar signals back from whence they came, not to camouflage the boat or anything, but so somebody who is pinging other ships for radar or pinging other ships to try to locate them will have a maximum likelihood of noticing the ship that has the retroflector. The next thing I want to talk about is refraction, which, as I mentioned before, happens when light passes from one medium into another medium. And I want to clarify that. Refraction happens when light passes from one medium to another medium with a different index of refraction. And as the light passes from one medium to another, its path bends or refracts. And this is a result of the change in the speed of light between the two mediums. So you can see an example of refraction over here in the image on the right. The light is actually being shined from down here in the corner, from this direction is where the incident ray is coming from, but the light comes into this boundary between water and air and then bends. So we will end up defining our angles that we need as this angle here and this angle there, where this would be the incident beam, and then this would be the refracted beam of light. Whenever refraction happens, there is also a small amount of reflection that happens as well. So we can see this green ray coming in this direction, and some of that green ray was sent off this direction as the reflected portion. And that reflected part will follow the law of reflection, so these two angles are equal to each other. But most of the time, when we're talking about refraction, we're not going to worry about the reflected part. We're just going to focus on the refracted beam that comes out up here. So I want to draw an image here to kind of drive this point home. So give me just a second to draw that. So I've drawn here a boundary between two different materials. So above this line, we have material 1 with index of refraction N1, and below this line, we have material 2 with index of refraction N2, which is the higher of the two. So N1 is less than N2. So if light comes from material 1 into material 2, the path of that light will bend. And it will bend in the following way. I'm going to draw my normal line because all of my angles are going to be measured from this normal line. And that light will bend closer to the normal line. And I want to label our two angles. Theta 1 will be this angle here, and theta 2 will be this angle here, both measured from the normal. So in words, when light passes from into a higher index of refraction material, it bends closer to the normal. And then we can look at the reverse of this as well. Maybe the light started off in N2 in our higher index of refraction material, and drawing our normal line again to help us know where to measure the angles we're going to need. Light, when it passes from a higher index of refraction material into a lower index of refraction material, will do the opposite thing. It will bend further away from the normal. So theta 2 and theta 1, which one is which depends on which angle occurs in which material. So notice that when the light was coming from top to bottom here, theta 1 was on the top and theta 2 was on the bottom. When the light's going from bottom to top, theta 2 is still on the bottom and theta 1 is still on the top. So 1 and 2 doesn't refer to the order of the two materials that the light passes through. It just matches with whichever material that angle occurs within. So both of theta 1s are measured between the light ray and the normal within material 1 with index of refraction N1. So all of the subscript 1s are above this line. All of the subscript 2s are below this line. So writing the equivalent statement in words for this. And there's a mathematical relationship between theta 1, theta 2, n1, and n2 that is known as Snell's Law. And Snell's Law states that n1 sine of theta 1 equals n2 sine of theta 2. Our angles we can just keep in degrees for this formula, and n doesn't have any units. So we are just going to be able to use this situation without worrying too much about what units we're dealing with and whether distances are measured in meters or centimeters or anything like that. So I want to consider a thought experiment here. I'm going to clear off some space here so that we can talk about it. For the sake of this example, we're going to have two regions, air up above and water down below. And let's imagine we are underneath the surface of the water and shining a laser up towards the surface. Let's say we're down here, and we want to imagine different angles we could shine this laser at. One of them is we could shine the laser straight upward towards the surface, so that our laser's path is aligned with the normal. And in this case, the laser will simply pass straight through without bending at all, because all of our thetas are 0, and sine of 0 is 0. Now let's imagine shining our laser at a little bit of an angle, so maybe we shine it this direction. Well, our light is about to pass from a higher index of refraction material into a lower index of refraction material, so the light here will have to bend away from the normal. Or stated another way, theta 1 here is going to be greater than theta 2. Well, at a certain point, we're going to reach a very specific angle of incidence here. At a certain point, we're going to reach the angle where we're going to give this angle within the water a very special name in a second here, but such that our outgoing ray is parallel to the surface of the water. So here, theta 1 is going to be 90 degrees. And when the outgoing ray is at 90 degrees, the incoming ray is called the critical angle. And we could find the critical angle for light by using Snell's law as follows. So we're going to have n1 sine of theta 1 equals n2 sine of theta 2. So one side of this equation will be air and one side will be water. So on the air side of the equation, we have the index of refraction of air, 1.000, times the sine of the angle within air, which is 90 degrees, and sine of 90 is 1. And now on the water side of the equation, the index is 1.333. And we've decided to call this angle the critical angle. So we can then solve for our critical angle, and we get a value of 48.6 degrees. So why that's significant, I want to draw one more ray here that's going to have to pass through kind of everything else. All of my mathematical work here. So let's imagine this ray, where we now have some incidence angle here within the water of some angle that is greater than our critical angle. What happens? So conceptually, we could look at our outgoing ray and say, well, our incoming ray bent even further from the normal, so our outgoing ray should bend even further from the normal. But you can't really get any further from the normal than 90 degrees. So it seems like refraction's not really going to work here. You could also look at this mathematically and say, well, let's take our index of refraction for water using Snell's law, 1.333, times the sine of, let's just pick an angle greater than the critical angle. Let's say 51 degrees. Would then equal the index of refraction in air, times the sine of whatever angle we are going to get in air. So I'll call it theta 1. So then we can actually work through this calculation and find that the sine of theta 1 has to be equal to whatever 1.333 times the sine of 51 degrees is, which turns out to be 1.036. So theta 1 is going to be the inverse sine of 1.036. So hopefully this is raising some red flags in your brain, because there is no answer for this. This is undefined. Your calculator will give you an error. So both our conceptual analysis and our math work are saying that refraction can't occur. So the question becomes, if refraction can't occur, what happens? So the only other option other than refraction is reflection. So it will reflect back in at this same angle theta as it was incidence at. So in words, this process is called total internal reflection. And if the incidence angle is greater than the critical angle, the light will reflect instead of refracting. And I mentioned earlier that every time refraction happens, there's also a little bit of reflection happening. The closer you get to the critical angle, the more of the light is reflected. But as soon as you pass the critical angle, 100% of the light is reflected. So what I want you all to do right now is to pause the video and try to think through this same process, but with the air and water reversed. We're still underneath this horizontal line that is the boundary between the two materials, but pretend the air is on the bottom and the water is on the top, and you're shining the light up from the air towards the water. And convince yourself that you cannot get total internal reflection in this situation. Try to convince yourself that total internal reflection can only happen within the material with the higher index of refraction. Now I want to explore total internal reflection a little bit and some of the ways in which we use it. But before we get there, I want to talk about a couple of interesting phenomena. One of them is directing your attention back to this first ray I drew here. Notice that this ray did not bend. This is one of only two situations for refraction where light passes from one material into another material where the light does not bend. And that's where the light ray is perpendicular to our surface, or the angle between the light ray and the normal is 0 degrees. But there's one other situation where light can pass from one material to another and not bend, and see if you can figure out what that would be. So I want to show you guys a cool YouTube video that demonstrates this property. So here is that video that I was talking about. And if you haven't figured it out already, the other way that light can pass from one material into another without bending its path is if the two materials have the same index of refraction. This is unlikely to occur on accident, but you can design specific materials so this happens. And this video gives a good example of that. So you can see them filling this cup here with a bunch of tiny little clear balls. And it will turn out that these little clear balls have the same index of refraction as water. So when they're surrounded by air, you can see the boundaries between them because the air has a different index of refraction than those tiny little water balls. But when you fill this up with water, it looks just about the same as an empty cup of water. So you can't see the boundaries between the little beads and the rest of the water because they have the same index of refraction. So when light passes from one of them into the other, work through your Snells Law formula. If n1 equals n2, then theta 1 has to equal theta 2, and the light, or the path of the light, does not bend. So as far as our eyes are concerned, it's as though this cup is just full of water, not the individual beads inside of there. And it can really mess with your mind when you can't actually see any of these beads. But they are there, they just happen to have the same index of refraction as water. And I just thought that was an interesting little side note that you guys might be interested in. Just wanted to show you another picture of total internal reflection that I found online. And this person is shining a laser from over here into this fish tank that's full of water. So we have air up here and water or some other material down there. And note that water here has the higher index of refraction, and the index of total internal reflection can only occur within the higher index of refraction. So, we draw our normal to the surface. We know for sure that whatever this angle theta is, it must be greater than the critical angle between this material that I'm assuming is water and the air above it. So this can actually create an interesting optical effect if you are within the higher index of refraction material yourself. For example, if you are laying at the bottom of a pool, holding your breath, looking up at the smooth surface of the pool, you get an effect called the Snells window that I want to show you here. So what we have here is a picture somebody's taken from the bottom of a pool looking up at a little swimming toy here up towards the ceiling. And when you look through this portion of the surface of the water, you just see the ceiling of the room in which this pool is located. But if you look off to the side over here, you're not seeing the ceiling anymore, you're seeing the reflection of the floor and walls of the pool. And what's happening here is total internal reflection. So if you are underwater here, if you have a ray that goes directly up from you, it will travel directly up into the air. And then if you have a ray that travels at a slight angle up from you, it will bend further away from the normal. And then at a certain point, you will reach that boundary where the refracted ray exits parallel to the surface of the water, which means that this angle right here is the critical angle between air and water, since that's the angle that gives us a 90-degree angle on the other side. So this means if you look any further to the side, and I'm going to draw these rays in purple, if you look any further to the side, we're now at an angle greater than the critical angle, so we just get total internal reflection back down. So Snell's window goes from here over to here. And Snell's window is the area of the surface that you see above you where the light passing through the surface there would be at an angle of less than the critical angle on the water side. So that is really, out here when we look out at the edges, what we're really seeing is what's going on with these purple rays. They're reflecting back down to the bottom of the pool, so we're seeing the sides and the walls and the floor of the pool itself rather than being able to actually see out of the water. One thing to note is that I've kind of drawn my arrows backwards here. If you're seeing something from your point of view down here, where this is a little eyeball representing your point of view, you should be seeing rays that are coming towards you. But one of the cool things about the ray model of light is that the path of light is always reversible. So we can reverse the direction of the arrows on any one of these rays and the path remains the same. So if light comes in perpendicular to the surface, it will pass through unscathed. If light comes in at an angle of about 90 degrees with the surface of the water, it will enter the water at the critical angle. Or if light comes up from the bottom or walls of the pool at some angle that is greater than the critical angle, it will reflect back down towards you. The other useful application of total internal reflection is fiber optics. Fiber optics are one of the ways that we can transmit data other than electricity, and a fiber optic cable consists of two components. The center here, this part, called the core, and a bit along the edge called the cladding. And what you have is the light ray following this path outlined in blue, reflecting off of each of these surfaces. So you can see that at each of those times the light ray encounters the border between the core and the cladding, it is reflected rather than refracted. So this means that total internal reflection is happening. And this is also why it's important not to bend fiber optic cables. Because if you made a very rigid boundary in this cable, like made it, the border comes here and then just bends like that, you might be more likely to have an angle that is not greater than the critical angle somewhere inside of here. Because every one of these angles that I'm labeling in red here has to be greater than the critical angle in order for the light to continue to remain within the fiber optic cable. And I want to do a sample calculation to show you how this all could work. So we're going to imagine ourselves a fiber optic cable arranged as follows. So we have a core with an index of refraction of n equals 1.55 and cladding with an index of refraction of 1.43. Hopefully you expected that the index of refraction for the core needs to be higher than the index of refraction for the cladding, because total internal reflection can only occur within the higher index of refraction material. So, if we shine light directly into the fiber optic cable, it will just continue along straight, and I've drawn this fiber optic cable, or this section of it, as straight, so there's nothing else that really happens there that would be important. But we also know, or could also figure out, that if we send this light in at too steep of an angle, too great of an angle from the normal, it might end up escaping through the sides of the cladding and the sides of the fiber optic cable like this, and this is bad. We don't want this to happen. This is not how fiber optic cables are supposed to work. So my question for you is the following. What is the largest angle the ray of light that's entering the fiber optic cable can make with the normal and still remain within the fiber optic cable, within the core? So, give this problem a go and see if you can solve it yourself first. So once you've given it a try, then unpause the video and see if your number matches mine. So first, I want to draw the path of this ray of light, just to get an idea what's going to happen. If the light had gone straight, it would have continued in this direction, but our light's going to enter a higher index of refraction material. It's going from air on the outside, where n equals 1, into the core with an index of refraction of n equals 1.55. So our light ray will bend closer to the normal and then hit the wall of the fiber optic cable on the top, as so. Well, if we want the light to remain within the core of the fiber optic cable, that means we need total internal reflection to occur at this boundary right here. And if we want to find the largest angle, the maximum, that means we're right at that borderline between the light remaining within the fiber optic cable and the light escaping the fiber optic cable. Which means this angle in here must be the angle that's right at the border between total internal reflection happening and not happening, which is the critical angle. So this is the problem we need to work out. So the first thing we need to do is find the critical angle between the core and the cladding. That looks like dadding, but it's really cladding. So using Snell's Law, the two sides of our Snell's Law equation will be the core side and the cladding side. So index of refraction of the core times the sine of the angle within the core equals the index of refraction of the cladding times the sine of the angle within the cladding. Well, we know the index of refraction of the core is 1.55, and this angle within the core is going to be our critical angle. And if the angle within our core is the critical angle, that means on the cladding side of the equation, in addition to the 1.43 for the index of refraction, we will have an angle of 90 degrees. And sine of 90 equals 1. So that means the sine of this critical angle is going to equal 1.43 divided by 1.52. And you can solve for that critical angle as 67.3 degrees. So we now know our value for theta c. And we've done our Snell's Law for the time where light encounters this surface here, the border between core and cladding. Let me actually make that circle in green instead. Because now we want to back up one step in time and look at this intersection of light between one material and another, and we can write Snell's Law here again. So this time we're dealing with a transition between air and the core. So our Snell's Law equation looks like this. The index of refraction of air times the sine of the angle within the air equals the index of refraction of the core times the sine of the angle within the core. And we know the index of refraction of air is 1, and that angle within the air we decided to call theta max. So we can fill out the other side of our equation as the index of the core is 1.55 times the sine of the angle within the core. And note that the angle we need within the core here is this angle. It is not the same as the 67.3 we just found, but there is a nice handy triangle here, a right triangle even, that we could use to quickly find the angle we need that I've labeled theta core here. So you could see that theta core has to be 90 degrees minus our critical angle. So our angle for theta core that we have here is 22.7 degrees. So we plug in 22.7 degrees down here, and we grind through the math to get our final answer that the maximum angle the incoming light ray can make with the normal to the surface of the core is 36.7 degrees. Any higher than this, and the light will leak out the sides of the fiber optic cable, thus rendering the fiber optic cable useless. That is everything I have for you for today. Sorry this one was a little on the longer side, but there was a lot of important and interesting stuff to talk about here. Thank you for watching, and have a good day.